Hello everyone. Today the topic of the presentation is mathematical models for devising testing and vaccination strategies. Testing and vaccination plays a significant role in containing the ongoing COVID-19. Testing can help us identify and quarantine infected persons with smaller cost, and vaccination can help us protect the most vulnerable people from being infected. Combining them together, we will be able to contain the spreading of the disease. We have spent quite a lot on testing. For example, a 1.5 billion program was initiated in the United States for providing 6 million tests per day. However, we didn't reach the goal. So in order to improve the efficiency of testing, we sometimes do pool or group testing, which means that we combine different patients' samples together and test them at once. The other way to go is to test based on social activity, which means that we only test those who are presumed to have at a higher risk. In our recent work, an agent-based model, which takes into account the contact time is used to allocate test kits. We can see that for each node, the risk is measured by the green bar, and we only select those who are presumed to be at the highest risk and get them tested. However, when the number of persons in our population is very large, the agent-based model may fail to work because we need exact interpersonal contact time data, and the computational burden may be very large if the persons in our population is very large. Therefore, we may need some mean-field population models. The mean-field models can efficiently define and compute optimal control strategies and can provide us with a more interpretable model. However, we must give up individual resolution, which means that we cannot select exactly those who are at the highest risk. And we may also give up some possible higher order degree correlations. We test on two network examples, the Barrow-Bassi-Albert network and the stochastic block model. In the Barrow-Bassi-Albert network, we can see that the ratio of population with degree k decays exponentially with k. And in the stochastic block model, we can see that most nodes have a degree that is close to the mean degree. We construct this effective degree testing model, which is based on the standard SIR model. So we divide the infected components into two subcomponents, the untested group and the tested group. The untested group can be converted to the tested group by testing. And the testing rate is the testing budget over the ratio of population. Also, each compartment is characterized by the effective degree L. So here, typically for untested group, their infection rate is much larger than the tested group because we're used to quarantine those who are tested positive. The goal is to reduce infections under a limited resource constraint. For instance, the daily number of tests is fixed. In order to minimize infections, we construct this loss function, which is an integration of the infection at time t multiplied by a factor rho to the power t. Here, rho is the discount factor, which penalizes later infections less than earlier infections. So we care about how to reduce earlier infections more. In order to minimize this L, we construct this Hamiltonian. We can see that for different subgroups characterized by different L's, the risk is measured by the red term, and the smaller this term is, the higher risk for that group is. So here are some results. We can see that for both networks, we tend to test those with a larger degree from the beginning, but as time goes by, when those people are almost infected, we turn to test those with a smaller degrees. In the Barrow-Bassi-Albert network, we can see that the effect of the optimal testing strategy is more apparent because for this network, very few nodes have a very large degree, and as long as we contain those nodes effectively, we can be able to contain the spreading of the disease more effectively. While in the stochastic block model, most nodes have very similar degree, so the effect of optimal testing is not so apparent. Vaccines play a major role in containing the spreading of the disease and protecting the vulnerable persons. We can also construct this effective degree vaccination model, and we assume that after receiving one dose of vaccination, the susceptible person can be converted to a person with a few immunity and converted to the recovered group. Also, given a constraint on daily vaccination doses, the fixed daily vaccination doses, how do we reduce the infections as much as possible? We also test for two networks, the Barabasi network and the stochastic block network. We can see that for the Barabasi network, it is hopeful that we can fully contain the spreading of the disease as long as we contain those with a larger degree from the beginning. For the stochastic block model, although we cannot fully contain the spreading of the disease, we can reduce the infections by a lot. As a comparison, we also perform reinforcement learning to study the optimal strategy. Actually, here we use the Pontryagin maximum principal approach to predict the possible optimal actions so that we can reduce the uncountable action set to a finite action set. However, because the Pontryagin maximum principle always gives the optimal strategy, we can see that the reinforcement learning cannot perform as well as the Pontryagin approach. However, it is still better than the uniform testing strategy, which means that the testing rate for different group of persons are the same. As our future work, we plan to consider content time distribution and the dynamic networks, which means that the interpersonal contact may change over time. Also, we plan to implement real data from real-world experiments and use more realistic loss functions to take into account more factors. Finally, we wish to consider simultaneous testing and vaccination as what happens in the real world. Thank you.